Need time to try your slide, ORIOL?
This moment.
Yeah. Oh, got it. Oh, it's live stream. Need time to try your slide.
Just a moment. Pak Yusuf.
Yes.
Okay. Yeah, it's on ready. Okay. May we start, Pak Dekan?
Yeah.
Yes. Okay. Professor ORIOL, can we start? Yep.
Yes,
Okay.
I'm ready.
Great. Okay, so good afternoon, everyone in Indonesia, and also good morning, especially to Professor ORIOL SERRA in Barcelona. Welcome again to Combinatorics today's series. This is the second episode of for this year, and I'm very, very happy to see you again. This Combinatorics today's series is organized by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institute Technology Bandung. In this series, we will bring you prominent combinatories throughout the world to give us a progress and the current development of combinatoric and graph theory. And in this year of 2021, we are very glad to be able to present you 10 prominent speakers from various countries to share with us in this Combinatorics Today series. They are from India, Spain, Japan, Australia, French, Germany, and United Kingdom. And this afternoon, we are all delighted and honored to have Professor ORIOL SERRA from the Universitat Politecnica de Catalunya, Barcelona, Spain, as our distinguished speaker. His talk will be on the Combinatorial Nullstellensatz, I hope I pronounce well, and will be moderated by Dr. Hilda Asiaton. Before I hand it over to Dr. Hilda, I would like to invite the Dean of Mathematics and Natural Sciences, ITB, Professor Wahyu Srikutomo, to give a welcoming speech. Professor Wahyu, time is yours.
Thank you very much, Prof. Eddie. Good afternoon here, my colleagues in Indonesia, and good morning to Professor ORIOL SERRA there in Universitat Politecnica de Catalunya, Barcelona, Spain. First of all, I would like to express my sincere gratitude to Professor SERRA for your time and your willingness to make this scientific communication and knowledge sharing happen. And of course, it is also an honor to us to have all the participants participating in this very important event. And as stated by Prof. Eddie just before, that today we will have the talk of Combinatorial Nullstellensatz from Professor ORIOL SERRA, and this talk is also a part of Combinatorics Today series, which is held by the research group of combinatoric mathematics or combinatorial mathematics, and of course, this is also a very good opportunity and a very useful bridge for our young students and also young researchers to have some insight and also communication with other prominent researchers or scientists from around the world. So, of course, we hope that all the participants may have fruitful benefits from this talk, and also can also make some discussion with Professor ORIOL SERRA about these combinatorial topics. And again, I would like to express my thanks, my gratitude to Professor SERRA, and also to the people from the Combinatorial Mathematics, Prof. Edi, Ibu Hilda, and others. I would also I would like to say thank you also to all the participants and welcome to this event. And Prof. Edi, I think that's conclude my opening speech. Very simple, but I'm very glad to have all of you, especially Professor SERRA here. Thank you very much. Keep safe and healthy.
Okay, thank you very much, Professor Wahyu. So now I would like to ask Dr. Hilda to share this talk.
Okay, thank you, Pak Edi. Good afternoon, everyone, and good morning to our colleagues from Europe, especially Professor ORIOL SERRA. It is my pleasure to be the moderator for this afternoon talk that will be given by Professor ORIOL SERRA. Before we start, allow me to share Professor SERRA curriculum vitae. Have you seen my slide? Yeah, okay. So I have summarized a short CV from a very impressive long CV from Professor ORIOL SERRA. So Professor ORIOL SERRA, hang on. I have a problem with this. Hang on, sorry. Yeah, Professor ORIOL SERRA graduated in mathematics at the Universitat de Barcelona in 1984 and obtained his PhD in mathematical sciences at Universitat Politecnica de Catalunya, Barcelona in 1989. He is a full professor at the Department of Mathematics of UPC since 1999, and he also the co-chair of the research group Geometric, Algebraic, and Probabilistic Combinatorics at UPC. He has several visiting positions in various universities across Europe and United States. His research interests in general are combinatorics, graph theory, and combinatorial number theory, but in particular, he's interested in isoperimetric problems, Ramsey theory, extremal and probabilistic combinatorics, and additive combinatorics. He has published around 100 papers and had been awarded many research grants from Catalan Research Council, Spanish Research Council, and European Union. He also has served some managerial duties as the chair of the Department of Mathematics at UPC 2011 until 2017, and also as the Vice Dean of Research of the School of Mathematics at UPC 2007 until 2011, and also the member of the Executive Committee of the Barcelona Graduate School of Mathematics, and the member of the Council of European Mathematical Society. Okay, without further ado, now I would like to invite Professor ORIOL SERRA. ORIOL, the stage is yours. You have 60 minutes.
Thank you very much. Thank you very much. So first of all, selamat salam to all of you. Thank you, Hilda, for your nice words, and thank you, Eddie, for giving me the opportunity of talking here. As you know, I have very good and fond memories from Bandung and from Indonesia in particular. I have very good memories. I'm very glad. I was looking for this picture that Hilda showed, which was taken in Bandung. So I did not find it, but I'm glad that you found it. And thank you, Professor Wayu, for your nice works. The words also for introducing. So yeah, it is a pity that I cannot be there with you, but it is also an advantage to have this system that it's easier to give talks in this way. So I will try to share my screen. Actually, I'm far away from you, so it looks like that the communication will be slightly slower than I was preparing. So let's see how it works.
Maybe we will turn off our video maybe to help.
So yeah, it may help. So let's see if it gets started. So I see in my screen, but I don't see yet in here. Oh la la. So I was
Okay, it's
Okay.
it's on now.
Finally, yeah.
Good. So we will go slightly slow. So I will try to talk more than see. I was wishing to use this device so yeah, I can write on the screen, which is kind of using a blackboard. And this is nicer. So my plan today is to discuss this algebraic method, which originally is called the Combinatorial Nullstellensatz. The name comes from a German result by Hilbert, which is called the Nullstellensatz theorem, which is a well-known theorem in algebraic geometry by Hilbert. And it was adapted for its use to combinatorial application by Alon, Nora Alon. So I think that it is better to call it the Alon method, which is shorter and easier to pronounce. So my plan is start discussing a little bit this theorem by Alon. This is will take short time. And my plan is to review some applications of this theorem to solve combinatorial problems. In particular, so I will discuss a little bit this list coloring because it's historically is the first application of this. Actually, the birth of this method was on a paper by Alon and Tarsi on list coloring. And then I will discuss some other applications, but in particular, so I remember that in Indonesia, there is a line of research around labelings of graphs. And actually, that's why I chose this topic, because this Alon's theorem provides a very useful tool to deal with some graph decompositions and labelings in general. I will discuss a little bit some results on this. And then I will just mention something because it's the most recent result that we have using this method in using not only to show the existence of some labeling, but count how many labelings are good. And I will conclude with some last words. So that will be the plan. So let me start. So what is this combinatorial Nullstellensatz? So it goes slightly slow, but it works nice. So as I mentioned, this is a this is an algebraic tool. And the algebraic tool is based on this theorem, which is that suppose that you have a polynomial on several variables, say x1 up to xn. And this polynomial has some degree d. So the statement of the theorem is that if you choose any non-negative integers, here called s1 up to sn, which add up to d, the degree of the polynomial, and then when you expand this polynomial, you find a monomial in which the variable x1 is to the power s1 and xn to the power sn, and the coefficient of this polynomial is non-zero, then the polynomial does not vanish in some point of the grid of the product, the Cartesian product of the sets S1, capital Sn, for every choice of these sets, as long as their cardinalities do not exceed the power of the monomial. So S1 has cardinality at most small s1, Sn has cardinality at most small sn. So that's the, so I repeat, you have a polynomial, you spot a monomial of largest degree, you look at the powers of the variables in this monomial, and you choose an arbitrary collection of sets with the only restriction that the cardinality of these sets is upper bounded by the degree is -1, and you will find a point in this Cartesian power where the polynomial does not vanish. Yes, for instance, I have this polynomial here, simple one. You expand this polynomial and you find that the degree is 2, and the monomial of highest degree is xy. The powers are 1 and 1. And then what it says is that if you take any set here of 2 points and here of 2 points, then you have this grid. Then you will find one of these 4 points where the polynomial does not vanish. So it is the result is kind of tight because, for instance, in this example, the polynomial do vanish if this is 0 and 1. So it do vanishes in these 3 points, and there is only one where the 0, 0, where it does not vanish. So that's the statement. That's what is called the Alon's theorem. He has a very nice paper in 1999, which explains many applications of this result. So how this result can be used to solve combinatorial problems. So let me start with a simple example, which is more or less on the base historically of the application of this method. So suppose that you have a cycle, say of 10 points, and to each point you assign a couple of numbers, real numbers or natural numbers. And now you would like to extract from each point, select one of these points, one of these values, one of those, one for each point. But what you want is that the resulting choices give you a coloring of the cycle. So no 2 neighbors are assigned the same color. So if all the numbers were 0 and 1, for instance, all the lists assigned to these vertices were 0 and 1, So I could choose only the even paired, nodes 0 and odd numbers 1. But what if here we have 0, 1, and here we have 1, 2, and here we have 2, 3? It looks like that the problem should be easier to solve, but it is not clear how to prove that such a choice exists. And so let's see how would we apply the polynomial method in this case. So the first thing is that it's an algebraic method. So we associate to every vertex variable. So there are 10 vertices, x1, x2, x10 will be 10 variables. x1 is a variable associated to the vertex p1, and so on. And now we construct a polynomial. So that's the first part of the method, to try to encode your combinatorial problem in terms of a polynomial. So the polynomial is, in this case, x1 minus x2 times x2 minus x3, and so on. And now we just realize that if this polynomial, so let me see if I have, no. So we realize that if this polynomial is non-zero, so if this polynomial in some point is not zero, then it means that x1 is different from a1 is different from a2, a2 is different from a3, a9 is different from a10, and a10 different from a1. So it means that these numbers a1, a10 provide good coloring of the cycle, the proper coloring. So this is the first step in this application of the polynomial method. We have a combinatorial problem, in this case to find a proper coloring of the cycle, and we encode this problem in terms of a polynomial. So this polynomial is non-zero if and only if the values of the variables are pairwise distinct in neighboring vertices. So that's one thing. Now, Alon's theorem, what it says is that this polynomial will be non-zero in some grid, in some choices of the numbers a1 up to a10. It will be non-zero if when you expand the polynomial, you find a monomial and look at the powers of the variables. Now here comes the tricky part of the method. So how do you expand this polynomial? You have to choose from each term. You have to choose one variable and multiply. So if I choose, for instance, the first variable in each of these monomials, and I multiply, I get this monomial x1, x2, x10. So this is a polynomial of degree 10. This monomial has degree 10, so it has the same degree as the polynomial. And what's the coefficient? Well, this was not the only way of obtaining this monomial in the expansion, because I as well could have chosen the other variables, x2, the ones which bear a minus sign, x2, x3, x10, x1. But you can just, by direct inspection, you can show that these two choices are the only ones in the expansion of the polynomial which would give rise to this monomial. If in some of these monomials here, I make a different choice than the greens or the yellows, then one of the variables will be raised to the power largest than 1. So there are only two ways of obtaining this monomial, and it happens that the coefficient for one is 1, and the coefficient for the other one is also 1 because it is minus 1 to the power 10, which is 1. So the coefficient of this monomial is 2, which is different from 0. So this depends on the field where you are considering this this polynomial. But if the field is, for instance, the reals or the rationals, if you have many choices, then 2 is not 0. And now the Alon theorem, what it says is that if you have choices of cardinality at least 2, so it should be 1 more than the degree, at least. Yeah, you have these choices and every one has cardinality 2. Then there exists a point here where the polynomial does not vanish. And as I have mentioned, this is equivalent to say that these values A1 up to A10 produce proper coloring of the cycle. So this little example is instructing because why cannot use the same argument if the cycle is of odd length? We know that it should not work for odd length because the chromatic number of C9, say, is 3. So we cannot get a coloring using only 2 colors for each vertex. And how is this happening? Well, the fact is that here, instead of 10, I have 9. Then the degree of this coefficient is 0. Sorry, the coefficient of this, because it's 1 minus 1. So it works automatically as it should. So that's beauty of mathematics, that if a method is correct, it gives the right answer. Good. So I think that this explains quite well what is the philosophy of the method. So I will now discuss some applications. Since I see that I was too optimistic, I will shorten some parts of it. In particular, I wanted to discuss the original, the source of this method. So this method was originated in a paper by Alon and Darcy to discuss problems of least coloring, as the one we saw. Yes. So I will remind you what is the least coloring problem. So you have a graph, and you assign to every vertex a list of possible colors, and you would like to find a proper coloring of the graph with the restriction that the colors should belong to the list assigned to the vertex. And the least chromatic number, as usual, is the minimum value k, such that if all lists have at least k colors, then you have for sure a list coloring. So this is a tricky problem because, for instance, here we have a bipartite graph whose regular chromatic number is 2, but however, the least chromatic number is 3. That's a standard example, but can be generalized to show that the difference between the least chromatic number and the regular chromatic number can be arbitrarily large. So how do you show that the least chromatic number is more than 2? you have to exhibit an assignment of lists of size 2 each one, for which there is no such choice. For instance, so here you may choose one for this color, and then what happens is that this one here and this one here are forbidden. And then you are forced to choose 2 and 3 in these vertices here. And then you see the surprise that here there is no choice for this poor vertex on the other side. That cannot choose either 2 or 3. So these problems are kind of tricky because your space, your combinatorial space, is the space of all possible list colorings, which in theory is infinite. Well, you can just argue that it is not infinite, it is finite, but still is very large. And then how to show that that a graph has a least chromatic number. And the idea of Alon and Tarsi was to use this polynomial method. So they used what is called the Graf polynomial, which is the natural polynomial that you may imagine. So again, every vertex is associated to a variable, and then you multiply all pairs of differences of variables whenever there is an edge in the graph. So this is called the Graf polynomial. And by definition, if this polynomial takes a non-zero value, it means that the assignment of these values to the variables produces a proper coloring of the graph. Now, if the polynomial has a non-zero value in the product of the lists that you have assigned to the vertices, then the answer is that you have a least coloring. Now, the only tricky thing here is, okay, so now according to Alon's theorem, we only have to spot a monomial of largest degree whose coefficient is non-zero, and the exponents are strictly smaller than the sizes of the list. And well, there are infinitely many graphs, so then it's not likely that you will find a method of doing this which is universal. So what Alon and Tarsi did was something which may look a little bit strange, but it is exactly associated to the way you produce monomials by expanding this polynomial. And the theorem, what it says, when it comes out, you will see it. Here is it. The theorem says that suppose that you make an orientation of the graph and you control the out degrees of the vertices in this orientation. And then the theorem simply states that if the number of Eulerian subgraphs which have an even number of edges is different from the number of Eulerian subgraphs. Eulerian means that the in degree and out degree is the same. So you look at the subgraphs and look at every Eulerian subgraph and count how many of them are with even number of edges and odd number of edges. If these numbers are not the same, then it will witness the appearance of a monomial which has non-zero coefficient. And therefore, you can apply Alon's method. So it may be slightly odd to say, well, I translated my problem to one which looks as difficult as the previous one, which is counting how many Eulerian subgraphs I have in some orientation of my graph here. But there are some applications which are, well, I will not discuss the proof of this, which is a nice illustration of what is the connection between the two. But I will skip this, and instead I will show some consequence of it, which was a long-standing conjecture, which was open at the time, which says that if you have a bipartite planar graph, so bipartite has chromatic number 2, the least coloring is only 3. And this 3 is tight because if you choose here this list, so this vertex, so this is K to 4, is planar and bipartite, and here you choose 3, 4 as the lists, and then here you choose 1, 3, 1, 4, 2, 3, and 2, 4. You see that there is no way of getting a proper coloring of this graph where each vertex chooses a color in its list. Yeah, for instance, if you choose 1 here, then here you are forced to use 3 and 4, and this poor guy gets no color. And why should the bipartite planar graph be a good candidate for application of this method? Is simply, and this is a combinatorial property, is that the planar bipartite graph always admits an orientation whose out degree is at most 2. And by using this theorem, now it's very simple to count Eulerian subgraphs, because since the graph is bipartite, there are no odd cycles. So every Eulerian subgraph must have an even number of edges. So the odd number, the number of Eulerian subgraphs of odd number of edges is 0. So the theorem applies. So let me show now another application of this method, which is also interesting and instructive. And it's related to what are called additive transversals, or in other language, how about rainbow matchings in graphs when it comes out. Here we are. So the general problem is the following. So suppose that you have a graph G, and you have an edge coloring in this graph. So the edges are colored in any way. And now a rainbow matching is a matching in which no two colors are the same. So there are many reasons why this problem is interesting, but one of them is that when the graph is the complete bipartite graph, and you have a proper edge coloring of the graph, you can encode this coloring by a Latin square, and a matching is a transversal of this Latin square, which means that you choose one point in each row and each column, and this is called a transversal, and you would like that the numbers in each transversal are pairwise distinct. And there is a long-standing, still open conjecture by Reiser, which says that every Latin square of odd order do contain a transversal. Now, suppose that the coloring is not completely arbitrary, but you just consider this complete bipartite graph K and N, and the coloring that you give to every vertex is the sum of the numbers which are in both sides. For instance, here, so you have 0, 1, 2, 0, 1, 2. So the red color is 0. So it's 0 plus 0. Yeah. Well, here I see that I made a mistake coloring the remaining ones, but this provides a coloring of the edges. And then what you have as a Latin square is the additive table of the group where you are working. And the problem is to find a transversal in this Latin square. And this is why it is called additive transversal. So Alon proved as one of applications of his method that if your group is the group of prime order P, then you always find an additive transversal, even of every fixed size. So you have two sets, oops, A and B, that they have the same cardinality. They are arbitrarily otherwise. So I take here 1, 2, 3, and here 0, 2, 3 in Z modulo 5. I now do the same thing. So for instance, 1 plus 0 is 1. 3 plus 3 is 1 also, modulo 5. So you get a coloring of all the edges. So here you have color 3, etc. And now the question is, does this sub table of the additive table of Z5 do have a rainbow matching? And the answer, by this theorem, is that the answer is yes, you will always find one. And the application here is again instructive for the use of the polynomial method. So if I want all the colors to be distinct, but I want them to be a matching, I have to add two conditions. Suppose that your set B has the letters B1 up to BK, the numbers B1 up to BK. And now for the other ones, I just use variables. And now I would like that the sum of each variable, each pi, xi plus bi, should be different from xj plus bj for every other j. So I multiply all these things, which will be non-zero, this product, if and only if xi plus bi is different from xj plus bj for every. So the sums are pairwise distinct. But then I would like also that the variables do not take repeated values. I want to have a matching. So I add this other one here. The product of these two monomials now encode the fact that I could choose a rainbow matching in this additive additively edge-colored complete bipartite graph. And now the trouble is to check if it is true that there is a coefficient of a monomial of largest degree with appropriate powers, which is non-zero. And here, this monomial is this one. So it is not completely, well, sorry. I said it is this one, but it is not yet displayed. Sometimes it's more lazy than others.
Okay, no problem.
Okay, here is it.
Yeah.
So that's the monomial, which has non-zero. So I insist that checking that this monomial is non-zero is maybe not trivial, but it can be done. So I have two motivations to discuss this problem. One is because it's related to conjecture by Snevely, which says that this same result applies to every abelian group of order. So this thing that we saw for Z modulo PP a prime should be also true for every abelian group of odd order. It is not difficult to check that if the group is of even order, then the statement is false. One reason I mentioned the result is that we could extend this Alon's method to the maybe more important class of abelian groups, which are cyclic groups of odd order n. And the second motivation I had is that this conjecture was eventually proved by Bohdan Arsovsky, a Macedonian mathematician. And the interesting thing is that he solved this conjecture after Professor Alon and a bunch of other people was fighting with the problem, and he solved it when he was an undergraduate student. So that's a good lesson for all of us. That it's a matter of finding the right idea. So that the proof is not trivial. So actually, it's amazing that an undergraduate student came up with the proof and used non-trivial things. So that says something of this man, but still it is showing that having good ideas is the best asset for a mathematician. So I see that my time is running. I will mention another result related to additive transversals. So Anna would have liked a lot to be here with us today, but he had some commitment and could not come. But at least I will just mention some of his results. So here it's a kind of inverse result of the same sort. Now here, what you are given is not, you are not asking that you have a matching such that the colors are pairwise distinct, but you insist that you want that the colors is a prescribed list. So you are given these colors and you ask, is there a matching in this additive colored complete bipartite graph such that the colors are precisely the ones that I'm prescribing? And the answer is yes, when P is a prime. So you are in a group of prime order. That's natural because in these applications of Alon's method, your starting point is always you have a polynomial with coefficients in a field. So you have to use a field. You cannot use an arbitrary group. So again, I will skip the proof. And so let me mention. So Hilda, when my time is over, you just wave and I will stop.
20 minutes, Oriol.
20? Oh,
Yes.
I'm still rich. Good, 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 good. That's wonderful. So you may be familiar with this conjecture of Wrinkles because I think that we have discussed this conjecture for a long time. It's an old conjecture, it's 1963, and it's very simple to state. And the conjecture is that every tree with m edges decomposes the complete graph of over 2n plus 1. Yes, so for instance, you have K5, and you take a tree with 2 edges, which now here you have not too many choices. And the statement is that you can decompose these the edges of this graph by edge disjoint copies of this one. And this problem gave rise to the at least one way of giving rise to these labeling problems. Because Kotzik, what he said is that if you can label the vertices of this graph by numbers and put this tree in here such that the difference of these numbers are different. So here the difference is 1, and here is 3. Then if you can do this, you can solve Wrinkles conjecture. And this is one of the sources of all these labelings, including these graceful labelings and all its variants, which gave a lot of material to all of us to investigate which trees to have graceful labelings. But in spite of the long efforts in this direction, what you could only do is to find a family of trees and say, look, these trees admit a graceful labeling, and for them, Wrinkles conjecture is true. But yeah, there are as many trees as people in the world. So this attack was not too successful. So I would like to mention 2 results here. One is again by Anna. Anna was using this polynomial method systematically for these labeling problems. And he could prove that at least Wrinkles conjecture is true almost surely. So if you take one tree at random, then this tree will almost surely, with probability tending to 1 when n goes to infinity, will satisfy Wrinkles conjecture. But at least there is this asymptotic proof of Wrinkles conjecture. And I must say that after all these years, yeah, so maybe almost 60 years, the conjecture was eventually solved by Richard Montgomery, Alex Prokofsky, and Denis Sudakov. Actually, the first 2 of these authors got European Prize of Combinatorics for this result, and they don't use the polynomial method. They use these more techniques, combinatorial techniques associated to the regularity lemma of Semerelli. So this conjecture is proved, except that it is only for very large n. Even if n is very large, the number of cases which have to be checked is finite. So maybe it can be done one day or the other. So I would like to mention that there is another conjecture which is, I think, due to Graham and Hackbist, which states the same statement, but in a somewhat easier case, which is the case where you ask a tree with n edges to decompose the complete bipartite graph KMM. The fact that the tree is bipartite and it's maybe more natural to decompose a bipartite graph. And in fact, the conjecture is much stronger. It says that every tree of edges not only decompose the complete bipartite graph, KMN, but every bipartite graph whose minimum degree is at least 10. And here, I think that perhaps people was not interested in this bipartite version of the conjecture, but the only result, general result, which we find in addition to all these results for specific families of trees, is again that every random tree decomposes the complete bipartite graph almasurely. So if you choose one at random, with probability tending to 1, you will be able to decompose the complete bipartite graph, which is an asymptotic version of this conjecture. And the proof again uses this polynomial method. I forgot to say that the naive approaches to Wrinkles conjecture through the combinatorial Nullstellensatz, at least the ones that I know of, they are not successful because you always can find a tree for which the associated polynomial has no non-zero coefficients of the desired form. So the plain attack with the polynomial method to the Wrinkles conjecture or Graham conjecture is not successful unless you invent some more, some different polynomial. Good. I chose another one. This is the one before the last. And there is also a kind of a personal reason to choose it in this talk in Bandung, because it's connected to the late Mirka Miller, which was a very fond collaborator of the mathematical school in Indonesia. And this one, the problem is also about labelings. There is a brave conjecture of Hasfield and Wrinkles, which says that every graph, distinct from K2, is antimagic. So what is antimagic? So you give a labeling of the edges of a graph, and what you ask is that the weight at each vertex, which is the sum of weights of its incident edges, should be all pairwise distinct. Yeah, for instance, here, these weights are, here is 11, here is 12, here is 9, here is 4, 3, 2, 1. They are all pairwise distinct. Now, the conjecture says that you can use labels. So here, for instance, this example had 6 edges. So you can find labeling using only M labels, as many as the number of edges. And I think that it is brave to conjecture that some property is universal through all universe of graphs. But Wrinkles did this conjecture, and they had some background. So, for instance, for some families of graphs, like stars, cycles, paths, complete graphs, Antimagic, and there is a list. Actually, there is a survey, a dynamic survey, which explains what is the status of this problem. The conjecture, to my knowledge, is still open. And one real exception of this conjecture is that instead of using M labels, so what if you can use M+1 or M+2 or M+3? And here is the result of Anna and Mirka, which says that for sure you never need more than more
Getting
than
slower.
Yes. Okay. More than M plus twice the number of vertices minus 4. I'm not very well aware of what is the status of this problem by now, but I think that it is the best bound, which is good for every graph. Yes, that you can use M plus twice the number of vertices minus 4. And in this paper, Anna and Mirka had many other results. Actually, it was published, this paper, when Mirka had already passed away, but I think that that was one of the last works that Mirka worked on, last papers. And there are several other results in this paper, and this one is perhaps the one which is simpler to explain. But again, I'm afraid that I should not spend too much time on it, but the idea is the same. So you want to encode this combinatorial problem such that every solution to your combinatorial problem would be associated to a polynomial non-vanishing. And since you want things to be distinct, then the natural thing is to use these van der Monde polynomials, which make which do not vanish unless the variables are pairwise distinct. And then you have to work out what is this polynomial when you expand it. And this is not trivial, and you have to work a little bit on this. It can be improved, the result for trees, where instead of using M plus 2n minus 4, you can use M plus k, where k is the number of inner vertices of the tree. For instance, a star would be M plus 1, and we know that the answer is simply M. This is not far from the... Okay, so I now just go to the very last topic I wanted to cover, which is about counting. So far we have talked about the existence of a solution to a combinatorial problem, which is related to the existence of a point where a polynomial does not vanish. Now, if we had a result which says that how many points this polynomial do not vanish on the grid, then we would have a counting result for the number of solutions to our combinatorial problem. And again, there is this theorem again by Alon, which says that you can have a result of this sort. It's difficult to appreciate here how strong is this counting result. So let me show one example where you can see that this counting result is very strong. And here the setting is something which are called group colorings. To simplify, I just use these modular colorings. So when the group is at n. So the thing is that you have a graph, and you give an orientation to this graph. And now what you want is that for every labeling of the edges by elements of this group, oh, this is wrong, it should be the other way around. So I color the edges with the elements of the group. So this is not good. And here I put any number. So for instance, suppose that I put 0, 0, 0 everywhere. That's legal labeling. I should find a coloring of the vertices now, such that difference is never the number of the label. So for instance, if I label every edge by 0, what I'm asking is that I should find a proper coloring of the graph, because the difference between two neighboring colors should be different from 0. Ta-chan, yeah. So this shows that these group colorings are a wide extension of regular colorings. There is some background on this thing, and I will mention two results which illustrate this strength of the polynomial method once more. And there is a result by Langhede and Thomassen, quite recent, from last year, when it appears, which says that every planar graph admits a Z5 coloring. So these group colorings are somewhat related, also can be related to the least colorings. And we know that the planar graph has least coloring chromatic number 5, so you cannot expect to have less than 5. But his result is that the number of such colorings is exponential in n. And so this is a strong counting result, which is obtained in their case by just combinatorial methods, elementary but very intricate. So we used this method with a team of Polish mathematicians, which also like this method very much. Bartek Beszek, Jarek Gryczuk, Gregor Grutowski, and Mariusz Sakai. And by using the polynomial method, we could see that it is not only exponential, but a much better constant, this 5 to the n4. And not only for planar graphs, but for K5 minor graphs. So you know that every planar graph is K5 and K3 free of minors. So if we only forbid K5, you have a larger class, which is completely characterized by a theorem by Wagner. And then you can use this machinery. But actually, it uses the same proof of Thomassen for the least chromatic number of planar graphs, which is a gem, a mathematical gem, and that's using it again. Okay, so I think that I cannot, I should stop here. So let me just say a few concluding remarks. So this Alon's paper that I mentioned at the beginning from 1999, according to Google, has about 600 citations. I think this is a very good paper to read. Alon writes papers very nicely, so it's not too difficult to read, and it has a host of additional applications in finite geometry, in algebra, in number theory, and of course in combinatorics that we have not discussed here. I should also mention that there are many refinements of this method, which adapt to multisets instead of sets, multiplicity of roots, the choice of this monomial. And I think that it's good to know about it because maybe it can be used in other problems that it has not been used yet. Okay. Terima kasih for your attention, and I will stop here. Hopefully not too late.
Thank you so much, Ariel. You're just in time. It's exactly 60 minutes. Thank you so much for a very interesting and inspiring talk. Now I think we may start the discussion session. It's already two persons asking question through the chat, but I would like to invite them to ask you directly. I invite Juanda Kelana Putra. Could you please ask the question directly to Professor ORIOL?
I see the question here,
yes.
which was in the chat. It was about the connection between the combinatorial Nullstellensatz and Hilbert Nullstellensatz. So Hilbert Nullstellensatz. Oh, sorry, Yuanda, you want to?
Yeah, maybe we can because we can chat directly to introduce himself. Juanda, still here? Are you still here?
Yeah. Thank you.
Okay.
Okay. First of all, I would like to thank Professor ORIOL SERRA and I would like to ask, is the relationship between the combinatorial Nullstellensatz and Hilbert Nullstellensatz? Thank you very much.
That's a natural question. And the relationship is that this Hilbert Nullstellensatz provide more or less the same answer. It is maybe not immediate to show the connection. So the Hilbert, what it says is that you have a ring of monomials which vanish in some, so which contains some ideal, so it vanishes in some points. Then this polynomial can be expressed as a multiple of the generator of this ideal. So you look at the monomial, which is the smallest one, which vanishes in the same points, and your polynomial would be a multiple, or it is generated in the ideal of these monomials. So the way I express this Alon's theorem is maybe not apparent, but he's using this idea. The advantage of the Alon's theorem is that it says that it is not a multiple, but exactly can be written as a polynomial like this, but it is weaker in the sense that you only look for polynomials which are of the form polynomials which vanish in the grid. So my explanation is perhaps not too transparent, but this connection is explicitly stated in this paper by Nora Alon. Maybe there it might be more clear. But yeah, there is a, that's why he shows this name.
Okay. Thank you, ORIOL. We have a little delay here. Yeah, for the second question, I would like to invite Muhammad Afif Rahman. Are you still here?
Wait. Hello. Hi, good afternoon or morning, Professor. Okay, I think I want to ask regarding your slide on the Wrinkles conjecture and the second conjecture one. I forgot the name, sorry. In the slide you mentioned that the results from those works use polynomial methods. I would like to ask how do we construct the necessary polynomials for so we can apply the Nullstellensatz methods. Thank you.
Okay. So here's the result. I will explain the bipartite case, which is easier to state. So you have a, you have a bipartite graph, tree, which is bipartite. For instance, this one, well, this is maybe a stupid example, but
It's fine.
and now what you do is you assign variables to one stable set and variables to the other stable set. And now you construct like a graph polynomial. So you would like that x1 and y1 have different values, and x1 minus i2 have different values, and so on. So every time that you see an edge, you write a monomial. Now this will ensure that the labels that you put in the edges are pairwise distinct. But now you have to add that the labels assigned to x1, x2, x3 are pairwise distinct. And the same for the y's. And this is your polynomial. So I mentioned that using directly this approach does not work because there are trees for which you compute this polynomial and you would find that the coefficients that you are looking for, magically, they are all zero. Which is kind of strange because it's it's algebraic combination, so it's strange that they are all zero. And so in both applications, you have to use this method with some additional knowledge. And the knowledge that you have here is that when you take a random tree, the number of leaves is large. So a random tree has many leaves, at least half of the number of it is a little less than half. And you combine this knowledge for random trees with an appropriate use of the polynomial method. But the polynomial is built in this way. The polynomial is kind of built straight away from your combinatorial problem. But yeah, sometimes it works nicely, sometimes you have to work more. Is it clear, Muhammad?
Okay, thank you very much.
Okay, thank you, ORIOL. There are two more questions here. The third one is from Pak Edi. Please.
Okay. So, ORIOL, thank you very much for a very, very nice and inspiring talk. So I think this method, Combinatorial Nullstellensatz, is very, very important and also very good methods. Yeah. My question is there any application if we use these methods to Ramsey numbers or finding Ramsey numbers or finding the existence of Ramsey minimal graph? Is there any application?
Excellent question. I don't know of any application to these Ramsey problems, and I think that I think it's worth trying to think about this, because it's true. I don't know of any application to Ramsey theory of this polynomial method. Well, polynomial method is larger. It's a larger topic. There are other uses of polynomial methods, and in these other uses, actually is I think that one of the explicit construction of Ramsey graphs, the best one, I think so, is by using polynomial methods, but not this method. So I think that that's a great idea to explore some suitable problem in Ramsey minimal graphs, which could be adapted to the use of this method. I have no idea. That's a very good question. Thank you, Eddie. We should think about this.
Yes. Great. Thank you, Oriol.
Okay. Thank you, Oriol. And the fourth question is coming from Lawrence Petrus, but he cannot on cam and cannot turn on his microphone. So I will read the question. Thank you for your amazing talk, Professor Serra. I would like to ask two questions. First, in the grid result, is the lower bound known to be optimum? That's the first question. And the second one, in your result in the last two slides, may I know how did you apply the combinatorial Nullstellensatz? Yes, please.
The answer to the first question is simple. And yes, the lower bound is optimal. I think that I made this. So this example at the beginning. So here you have. I don't know if it is visible yet. This polynomial. Here we have degree is 2. The only monomial of degree 2 is xy. The powers are 1 and 1. And if I look at the grid of these 4 numbers, there is only one in which this polynomial do not vanish. So here in 1, 0, if I put x1, y0, polynomial vanish, 0, 1 as well, 1, 1 as well, 0, 0, no. Now, if you take any, for instance, if you take here one set containing 2 elements and the other one containing 1, oh, sorry, here. So if you take this one, then polynomial vanishes in 1, 1 and in 0, 1. So the bound is tight. And for the second question, it's more difficult to answer. So let me see if I find some. So let me. So I don't know if you are familiar with the Thomason proof, but you have a triangulation of a graph, planar graph. something. And then Thomason's proof, what it says is that if you have two available colors in each vertex of the boundary, and you have inside at least 5, say, then you can have a coloring of this graph by using these lists. So the polynomial method here applies by saying that you define something which is local at every vertex, a polynomial here, and you substitute the size of the list by the degree of the polynomial. And you make an algebraic version of this proof, saying that if at each vertex here you are allowed to have a polynomial of degree 2, and inside a polynomial of degree 5, well, here, these monomials are monomials involving this vertex. Then if you have this, then you can apply the same type of induction that it is used in this Thomason's proof. So you substitute lists by degrees of polynomials. So the polynomial is always the same. The polynomial is this graph polynomial. And now what you are saying is that you select the monomials of this polynomial which involve the vertices which are in the outer boundary, and you put a limit on the degrees on this for these variables. And then inside you can have larger degrees. And then you proceed exactly as in the proof of Thomason's for the list coloring. I forgot to say something that for this counting, there is a condition, and the condition is that the polynomial does not vanish in a grid. So the statement is, if polynomial does not vanish in a grid, then the number of solutions is at least something. So here you work in 2 steps. So first, you show that the polynomial do not vanish by using this argument, and then counting, apply this counting version, and you get this exponential number of solutions. I hope that I replied more or less properly to Lawrence.
Okay. Yeah. Thank you so much. Yeah, it's very interesting and inspiring discussion, but because the time limitation, we must end our discussion here. Thank you very much, Professor ORIOL SERRA. We give a big applause to ORIOL. Thank you so much. And I will return the stage to Pak Edi. Thank you, Pak Edi.
Okay, so thank you, Wilda, for chairing this session. And thanks again, Professor ORIOL SERRA, for nice lectures and very interesting. I think everyone will enjoy these lectures. And
thank you very much for inviting me. It's always a pleasure to be with you.
Right. And I would like to present you some certificate for being a speaker of our series. So let me show you. I will send you this certificate. So thanks again. So we are
Thank you very much.
really thankful, to Professor ORIOL SERRA for sharing this very nice topic. Okay, so I will send you this certificate, to.
Thank you. I will, and I will learn how to make this nice background. So it's a pity that I did not know how to do it.
So no, before we end, we have a photo
Photo.
session.
Yes.
Yeah. Okay. So please open
Yusuf?
up your camera.
Siapa ini?
Then let me.
Hello,
view.
Oriol. How are you?
Hello.
Ada Pak Slamin. Okay.
In good shape.
First page, ya.
Still smoking?
No.
Halo Pak Oriol.
Ada Bu Kiki,
Slamin, you are
Oriol.
Virtually.
I got heart attack.
Okay, second page.
Hey, Kiki, good to see you.
Lain Pak Agung kok nggak
Long time
kelihatan
no
tuh
see.
wajahnya tuh. Okay, third page already. Okay, yes, ya.
Ada Pak Joy sama Bu Andrea juga, Pak Edi.
Ya,
Andrea
thank you very much, Bu Andrea. And also, siapa ini? Banyak sekali ini. Ada Pak Surahmat. Ada
There's also Balmasida here.
Hola,
Yes.
hola, Prof. Oriol.
ada Pak Wayan.
Wow.
I'm
Nah,
Wayan. Hola, do you remember
Pak
me?
Wayan. Jadi
Pak
gondrong.
Wayan rambut baru nih.
Yeah,
Baru.
I'm Wayan.
Hello,
From
Joey. How
Palu,
are you?
Prof. Oriol. Nice to meet you.
Hello, good to see you.
How are you? How are you?
so
How are you, Oriol? How are
all
you?
the members of the Combinatorial Society in Indonesia is here now.
Good. I'm happy to know a large number of you.
And also from the Philippines.
And also the
Ah.
Philippines.
And also from
Yeah.
the
They're watching. My students are on the YouTube. I think.
Okay.
Oh, hi.
Oh, you.
Okay. So, okay, yes. So, next 2 weeks we will have Professor siapa? Aha, lupa lagi.
Forgot.
Saya juga nggak
ingat.
Next 2 weeks. Let me see. Okay. Iwa. So next 2 weeks will be okay. We will have a Professor Ian Wanless
Okay.
Yeah,
Oh,
From Melbourne.
from
Melbourne, Monash University.
from
right?
Indonesia.
Monash University.
he will talk about these Latin squares,
Yeah.
Yeah.
transversal Latin squares.
Okay. And then afterwards, we will have Professor Akira Saito the next month.
Okay, so please send announcements to me. So
Okay.
I would like
great.
to.
Yes, sure.
Thank you.
Yeah. So we will
you
extend
put
the
me
invitation to
on the list.
everybody. Yeah.
Yep.
Yeah.
Okay. So terima kasih
Okay.
semuanya.
Terima
Thank you very much.
kasih.
Terima
Thank you,
kasih.
Oriol. Very nice talk.
Thank you, Oriol.
Goodbye.
See you all.
Bye.
Bye.
My best regard to Anna.
Yeah.
I will.
Okay.
Also send my warmest regard to Anna.
Yeah.
I will. Sure.
And everybody at UPC.
Yeah.
I will.
Everybody in
Yes.
UPC. Yeah.
It was very nice to meet you all. Really. Thank you very much. Bye.
Okay.
Bye.
Bye.
Thank
Bye.
you.
Oke ya.
Terima kasih semuanya, Pak
Ya.
Presiden.
Dear Pak Edi.
Terima kasih.
ya.
Sampai jumpa ya.
Semua Joy,
Ya,
Prof.
Ya.
Edi.
Panengan.
Andrea. Thanks a
Bye,
lot.
Andrea.
Yeah.
Andrea. Bye,
Bye
Joey.
semuanya.
See you next week.